Okay, so we were looking at codec for the DNA storage, and I was describing some of our work, especially the Gole code business, and then I am going to discuss about the constraint coding. So I'll give very brief background about constraint coding. Then I will show what we have done, and also I will give you one interesting problem in that area. So this is lecture 8. We were looking at let me go to the slides where we left last time. Yes. So as I mentioned in the last lecture, I was about to tell you these two approaches, and these were the earlier approaches that we have contributed in this area. DNA Gole code, DNA Gole subcode, constraint coding. So first, I'm going to talk about the Gole code. I think I have already talked about it, but one key result I would like to tell you there. So we identified bunch of ternary codes, and then we picked up second one here because length is 11, total number of code was 256, and distance is 5. So it can correct 2 errors, and it's a ternary 0, 1, 2, right? Here is the Gole code business which we talked about. This is the subcode which actually we used. Okay, so now actually, as you know that whenever we have this string of some text or whatever or image convert into ASCII values, these ternary things. So we have used here this Gole code notebook, we call it, and then we do all this further, for the dot and comma and so on text file, and then should be multiple of 99. So we pad it with these zeros. So here we have something like this. Okay. So from this ternary string of the length, we get a string of ACGT, and as I mentioned to you, a key property that we wanted to have using this non-homopolymer map, that this map is having the property that the corresponding DNA string, there is no repetition of A or C or G or T. So AA is not there, CC is not there, those kind of things are not there. Now, we also observed certain other interesting properties of this map, and I'm going to describe you that now. First of all, this map is not unique. There are many other maps possible, so which you can, I guess, you can, use any one of them, and they have the same properties actually. First property, that if you take XDNA code word, you take XDNA, a string of ACGT, and right, so you are about to send it through a channel. I mean, you are going to store it, and some errors happen, and YDNA is received. Now, YDNA is received, so obviously, suppose T errors have happened, right? So distance between these two will be T. The Hamming distance will be T, right? T bits are flipped. Okay. Now, if we for this XDNA and YDNA, we go back to the map, reverse it, and get the X and Y, the ternary vectors. You will observe that the distance between ternary vectors cannot exceed 2T. Okay, this is the property of the map. Okay, so cannot exceed 2T. So, for example, in this case, or sometime it is exactly 2T. For example, if XDNA is this here, YDNA is this, corresponding X and Y is this, the Hamming distance turns out to be. Here the distance is 2, and in the case of ternary, we have the 4. Okay, so now this is the first property. Now I am going to show you how we can correct 2-bit flip errors. Why I am calling it double layer? Because on one side I have a Gole subcode notebook with distance 5, which can correct 2 errors on the ternary side. Okay, but what I want to correct 2 errors on the DNA side. Okay, and how do we do that? The first one, if X DNA we are writing, and suppose Y DNA is read, right? X DNA we are writing, Y DNA is read, such that case 1, there is one bit flip, there is only one error, suppose. One bit flip happened. So that in that case, Hamming distance between X DNA and Y DNA will be 1, right? And when you go back, the distance between X comma Y ternary will be 2 because of the previous lemma, right? It will be 2, right? Now, since distance is 2, we can correct errors because it's a ternary Gole subcode, right? Distance is 5, so we can correct 2 errors, right? So if this distance is 2, we can always correct it, right? So that means 2 errors have happened, we can correct it using the maximum likelihood decoding of the ternary Gole code, right? So we are done. What happens in the other case? Suppose there are two bits at the DNA side, 2 bits error, basically 2 bits flip. Now, I'm going to give you an idea. So basically now, in this case, what will happen? So remember, if you look at the Hamming distance property, if the code is suppose is C, I'm talking in general. If suppose the Hamming distance is at least 2t plus 1, suppose, that means it can correct t errors, right? Now, how do we approach the proof? The proof is like that. If X is sent, Y is received, T errors occurred. So distance between X comma Y is T, right? Now, Y is received. Now, if you look at the code book and I look at, any other code word. So I am comparing Y with all the code words, right? So distance of Y with X will be T because that is the actual word which was sent. And for all other code words other than X, distance will be more than T actually, because this is the nearest, the smallest one. Okay. And that is the approach of if the distance is 2t plus 1, we can actually do this proof, So basically there, the proof goes like this. Assume T errors occurred, distance between X comma Y is T, right? Now you pick up any other code word W in the whole code. So the distance between W comma Y will be more than T. That you can prove. Suppose it is not, you can use triangle inequality to show that because distance, the minimum distance is 2t plus 1, you will arrive at a contradiction to that fact. Okay. Okay. So that is the key thing. Similar idea we are trying to bring it here. Okay. So what I am going to do. So if the distance between X DNA and Y DNA is 2, okay. So we are going back to the ternary case. So in ternary case, what will happen? There will be a ternary vector X and a Y such that distance between X and Y could be at most 4. The lemma, right? This much we know. Any other information I have? So now I'll just do what? I'll write down the case, what happens here in this case. So we have this read-write channel, X DNA is stored, Y DNA is received. And we are saying 2 bits flipped, 2 bit flips, right? So I can write down, so basically X DNA, somewhere there will be Y DNA and W DNA. So W DNA is other than Y DNA, I'm saying. So basically I can write down one more line here saying that. Now what we are claiming, so now you see that X DNA was sent, Y DNA was received. Distance between X DNA and Y DNA is 2, right? Because 2 errors happened, right? Now what we are claiming here, that for any other W DNA other than X DNA, the distance is more than 2. Okay. The same idea we are bringing it here. In this, and why this is happening? Because of this beautiful property of this map actually. I'm not going into too many details, but you can look at it, look at the notebook actually. This happens here. So now I'll give you an example to show you how it works, Now you look at this example here. X DNA was this, Y DNA is received. So X is this, Y is this. Hamming distance between X DNA and Y DNA is 2. They differ at 2 places, right? And the distance between X comma Y is 4. You can see that, right? Now, we are looking at, now we are computing. So Y DNA is received. I'm computing the distance of Y DNA with every vector in the whole set of DNA strings, right? So the first one, distance turns out to be 10. So W DNA is a vector which I am, any arbitrary vector in the whole set. I'm just comparing the distance with y-DNA is the receipt vector. Distance with the, when the vector is this TACAG, whatever the first one, you distance is 10. Second one, it is 2. All these 4, 6, 7, and so you see it is more than 2. So only this vector is having distance 2, the second one, right? So that means that is the actual word which was sent, right? That is our actual X. Basically, this is the one which was sent, So this is our simple distance decoding we are again applying here, so that we can correct 2-bit flip in the DNA area, right? If it is 1-bit flip in DNA, we are going to the ternary and we are correcting using that property, right? And if it is actually 4, so actually, if it is distance is 2, if they are 2-bit flip, then we are using this mechanism. We can see that we can computing the distance, it is more. So actually, that is the one which was sent, right? So this is a key idea about correcting errors. Code. Okay, so once we can compute by looking at the chunk architecture and counting, we will arrive at this nonlinear equation. X is the number of bytes per gram of DNA. L is the length of chunk without chunk index. Okay, length of the error correcting code is equal to N99 is capital N. And so basically, we can compute the capacity by solving this equation. The DNA storage capacity turns out to be 115 exabyte per gram of DNA. So I am leaving. You can read that paper for calculations. I am just skipping the calculations right now. Okay. We also tried plotting all the graphs, basically in terms of scalability, So we see that 11 to 56, 5 support there, and all other codes which we identified initially, and the Goldman one. So you can see in terms of the how much storage is required. So this is really kind of exponential, the Gole scheme, and all ours are almost straight line like this, So comparably, they are good, obviously, because we are not compromising much on the. I mean, we are reducing the length, and actually, still we are able to correct 2-bit flips. The question is this: that do you think that you can come up with another beautiful scheme which can correct? Right now, we are focusing only bit flip error. Can you focus on insertion or deletion? That kind of error, right? This is an open problem for you. Do you think that you can, from this scenario, maybe modify something and you can correct insertion, deletion? Okay, insertion, deletion, or substitution. I mean, to make the matter more simple, assume that we are only looking at deletion. How do we correct deletion bits? Okay, and if you can come up with a new scheme, new architecture, and see what is the capacity and so on, those things you can work it out. So it's really, we just looked at 2-bit flip, that's all. But you can look at other error models here as well. Okay. So why we took the 11 to 56 5 code? Because you see that if we plot the code rate, so if we are going here, code rate is decreasing, when we want to correct more and more errors, right? So when t is equal to 2, though we can correct 2 errors, but the code rate is pretty good. We can use this, but then the code rate will be less. Okay, so there will be obviously some trade-off in terms of efficiency. So I would say that's why we picked up this, but of course you can pick up any of them. So that is pretty bad. This is the kind of good one. For one error correction, obviously it's almost, a little bit more than half, so which is okay. Okay. So the challenge is to construct a code which is having code rate very close to 1, right? That will be a very good thing, right? From the engineering point of view. So this is the obvious. And now we can see that we have in that implementation, you can see that all these original files which were done by Goldman scheme, in our case, it is quite low in terms of number of nucleotides or even the number of chunks that are used to store the information, right? So this is better. Okay, now we look at the second part that we did. So after this paper, I think we interacted with Professor Vanit Agarwal at Purdue, and then we come up with this scheme of constraint coding. Constraint coding is very beautiful thing, and all your CD, DVD, Blu-ray days, all these optical storage devices uses constraint coding. It's a very common and very beautiful thing. I'll give you some motivation. Luckily, I found yesterday, one nice paper by Keys Imik. Keys Imik is as I mentioned to you, he has almost more than 1,000 patents, 1,100 maybe something like that on storage. Okay, so you will find patent about his patent on everything, and most of them are related to constraint coding. It's a very nice coding scheme. So when data is written on CD, what happens actually? It's the optical disc. Laser is pointed to create the dots, right? Or DVD, or Blu-ray disc, all those things. So all these storage devices uses or even flash memory that you insert in your this thing, that also uses constraint coding. It's a very beautiful area. So I'm now going to give you some brief idea about constraint coding. Okay. And for the DNA storage, I would say that though people have done some work, still a lot of things are open. Okay. I mean, you can really do a lot of work in terms of writing a paper or publishing a paper, or maybe filing a patent or something that is possible in this area, right? So let me show you a few things here. This Here is he's Imik. He's known as father of storage, basically technology. He's right now having his own company, Turing Inc. He's in Netherlands actually. So we wanted to invite him here at some point of time, but I think he was busy. But anyway, so I show you a problem that, so after our paper, he pointed out one interesting thing to work on. I will give you that thing, and maybe you can look at it and see if you can simplify it. It's something very simple. Okay. So, I mean, something very, you have to invent new way of counting actually. Okay. So recently he has written a review paper in IEEE Communication Society magazine, Innovation in Constraint Codes. So this paper, September 2022, right? So this month only, very latest. So I have taken few things from his paper. I mean, this next couple of slides are based on his paper only, so that you can see. So now you can see what is happening here. Why constraint coding? So there is a very early way. A constraint communication system. So right now what we were doing in our error correcting codes. There are certain number of bits we encode. So suppose k bits are there, you encode into n bits and send it, right? So they are fixed, right? And bit flip is there. Bit flip is happening, right? So they are free from any kind of constraints. But what are the constraints now? If you look at this picture here, this gentleman is communicating through fire signal. So through smoking signals, right? So he's generating smokes and sending it across, right? So if there is a one puff of smoke, that means one. No smoke, so that means zero. So binary encoding you can do actually, right? So 111 000 like that you can send, right? This is a early example of constrained communication system. So what happens? A long run of zeros, when absence of smoke puff, puff is not there. Okay, may burn the blanket. So basically, what you're keeping it there itself, right? So it will burn, right? Burn the thing. And why this example? Because the burning is the way the laser things are pointed out on the storage device. So they are also the same thing. That's why they are always burning disk. Data is stored by burning the disk. Okay, all those disks. That's why that. It's a very nice example he has taken actually. In fact, there is a video lecture also available. You can watch. I will show you the link. Towards the end of the lecture. So this will destroy the transmitter, right? So if it may burn, right? So there is a problem. So basically, how do we correct errors in this kind of scenario? So basically, still we are having those binary strings, but now there are certain constraints. The kind of constraints. What kind of constraints are there? So as you can see that, in 1990s, the area of optical disc recording, also known as burning, there was a patent granted actually, you see, just for doing this actually, in order to extend the life of the laser, it is desirable to select a code such that the number of laser pulses needed for recording is minimized. So how do you design such an efficient thing? That itself is a patent, okay? So that is how, so in the storage thing, okay? So this patent, you can look at it on your own, okay? And also, Shannon, although gave some idea about these kind of channels, we now call it constrained channel. And at that point of time, he called it input restricted noiseless channel. So input is restricted in some way, okay, in these channels. And I think that is the original paper, as I think some of you might be knowing that this is the remarkable paper, seminal paper of Shannon, where he talked about information theory ideas, right? That you can construct codes which can correct errors, okay? Both of them are very important papers. I mean, that's first one is the patent, the second one is a very important paper. So basically, how does this look? You know, I think Shannon gave an example of this kind of channel. You know, when you do this telegraph, you send messages, right? So dot 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 d d d right, d d d da da d, right? It's like that. So d d d da d da d, like that. Okay, so those kind of communications you send. So this channel, so dot or dash is there only. So a letter space, so there are constraints. The kind of constraints are a letter space may not follow a word space and vice versa. This kind of constraint, if you put, it becomes a constraint channel. So initially, Shannon called it input restricted noiseless channel. This is the channel. Of course, there are much more theory about these kind of channels. I'm not going to describe any of those things too much, but I'm giving you some brief idea about it. Now, I think I will also give you some brief introduction or some terminology, at least, or some examples, so that you know what are the constraint codes. Okay, so. Okay, so basically, a couple of definitions. The number of consecutive zeros or ones is called as run length. So if in the string consecutive zeros are there or consecutive ones are there, we call it run length, right? And length could be something, that's okay. Now for certain applications, run length of the, run length of the sent message lie between some minimum value and maximum value. So run length means consecutive zeros or consecutive ones should have a lower bound or upper bound, right? Depends on the application. Okay, so I'm talking in terms of in more general things. What is constraint system, right? So now I am going to define what is known as decay sequence, which is very common terminology here. So suppose x is equal to x1, x2, x3, x1, x2, xn in n binary bits, right? So n bits, 0 or 1, n bits, right? Now we define what is known as decay sequence. A decay sequence. So in the decay sequence, so there are two things: deconstraint. What do you mean by deconstraint? That we have consecutive ones. Consecutive ones are there, and they are separated by at least zeros. Deconstraint. There are consecutive ones, but they are separated by at least d zeros. Okay, this is one of the constraint. Okay, and there is also kind of we also say that a k constraint. K constraint means we have these number of zeros cannot exceed, these number of consecutive zeros cannot exceed k. Okay, so k is kind of upper bound of the number of zeros. At least d zeros and at most k zeros. Between any two consecutive ones, on the zeros we have this property, right? At least d zeros and at most k zeros. This is a constraint, right? Of course, one can develop the whole theory for whole things, but I'll give you one specific example. Initially, we will assume that only D constraint, right? I'm not worrying about K constraints, and then we will see what can be done. Okay, whole theory you can read if you really want to read more about the constraint course. Okay, so essentially DK sequence consisting of two constraints, D constraint and K constraint. Okay, so consecutive ones are separated by at least D zeros and at most K zeros. Okay, fine. Now we define what is known as run length limited sequence, RLL sequence. Run length limited sequence. So you can construct from these decay sequences a run length limited sequence. What are these things? So these sequences, I'm just giving you an example, not too many things, but suppose we have y1, y2, yn. So y is equal to y1, y2, yn. Again, n bits are there. Okay. So these are known as run length limited sequence. If we can construct it from these decay sequence like this, yi is equal to yi minus 1, exclusive for xi, with y0 is equal to 1. Right? So we need to have a x first. X is a decay sequence. Right? What is decay sequence? Consecutive ones are separated by at least d zeros and at most k zeros. Right? That is the decay sequence. From that decay sequence, we can construct a run length limited sequence, RLL sequence y, like this. Okay. So basically, obviously, you can see that here it is I minus 1. So we require y0 value, right? Y0, and then, we'll give you, add it to x1, and then keep on doing exclusive OR. So if, for example, if x is 0, 1, 0, 0, 1, 0, 0, 0, 1 is a decay sequence, then y turns out to be 1, 0, 0, 0, 1, 1, 1, 1, 0. Okay. So from decay sequence, I can construct RLL sequence, right? Run length limited sequence. And so the run length of these, of the RLL sequence, lie between D plus 1 and K plus 1. So D or K values we can get from X, DK sequence, right? And the Y will have this kind of property. The run length of the RLL sequence lies between D plus 1 and K plus 1. Okay. So these are the basic terminology. So now you know what is DK sequence, you know what is run length limited sequence, RLL sequence, and I gave you one method of constructing them. So now basically the question is, as you know that for any communication channel, we should have a capacity. Again, without giving a proof, but I'll give you a formula for the capacity of a constraint channel. Okay, what is the capacity of a constraint channel? Capacity of a constraint channel C is limit T approaches to infinity 1 over T log of 2 base n of T. What is n of T here? Number of allowed signal sequences in the time interval. So how many signals are allowed? Time interval T, right? So that is n of T. Take the log and then compute this value. This is the capacity. I'm not giving you any formula or any this thing, but at least mentioning you the form, the proof of this, but at least mentioning you the formula, right? So this is the capacity of a constrained channel. Okay. Now again, we can simplify this formula for if you take only D sequences. Suppose we drop the K condition. Okay, only D sequences. Then we can simplify this. So I'm just mentioning that So suppose NDN is number of D sequences of length n. So K is dropped, K constraint is absent, right? We do not have that constraint. It's dropped. Only we are taking number of D sequences of length n. So of course, one can count how many D sequences are there of length n, right? I mean, you can do one by one, but of course you require a formula for that. I'm just mentioning a result that ND of n is approximately C times lambda raised to power n. N is greater or equal to 1, C is a constant, and lambda is known as growth factor. Actually, lambda lies between 1 and 2 and is the largest real root of the characteristic equation z raised to power d plus 1 minus z raised to power d minus 1 is equal to 0. Of course, you have to believe me that these are the results, Anyway, for such D-constrained channel, the channel capacity CD is equal to log of 2 base lambda. Okay. So this is a general, some idea about capacity, why we should worry about it. We can actually compute certain values of this, You can see that I think some values I can mention here. You see that when D is increasing, so we are looking at only D constraint channel, K constraint I have dropped, okay, only D constraint channel. So when D is increasing, capacity is decreasing, right? So obviously this seems to be obvious thing, now you are actually, when you're putting more and more constraints, the capacity will decrease anyway, right? Also, the D constraint thing can be described by a state transition diagram, so this is a state transition diagram for a D sequence. So these are the states, so 1, 2, 3 up to D and D plus 1. Now you see that for all other states except D plus 1, it emits only 0, and D plus 1 will emit 0 or 1. Okay. So this is the D constraint channel. So these channels are used for constructing constraint codes. Okay, I mean these kind of state diagrams are used. I think you might have looked at. Oh yeah, so you may not be knowing the convolution code, but you know about the finite state automata, right? Those kind of things are used here for the construction of these codes. I'll give you just one example here. Here is, you see, so there are 3 bits as a input, certain bits. So basically in these kind of finite automata channels or finite automata thing, certain bits are going, so K bits are going and bits are coming out using this machinery which will generate the whole streams, right? So in this example, D is equal to 1 block code, 3 bits are going and these bits are output. Okay, so you can also write, I mean, I think it will be interesting for you to basically construct the state diagram for this, how do we do this, these things are, so these are, you see, the source is all possible 8 bits, right, of length 3, because K is equal to 3 will go, right? So I should know if 0, 1, 1 goes, what should be come out, right? So it's a very interesting thing to see that how to construct. So this output is having 8 bits. One thing is obvious, you can see that the first column is all 0, right? So maybe you can drop it as well, but while doing the calculation. But anyway, so this is the whole thing that now you see that D is equal to 1 everywhere, right? There is only 1. D is equal to 1 everywhere in the right hand side. Okay, so the constraint is 1, right? So the thing is that how do we construct this kind of code? This is a thing. I mean, one has to think like that when these codes were discovered something around 1963 or so, 63, 64. In fact, the first machine that was used by IBM, they also used these kind of codes, the huge machine for storage. It was constructed very early stage. I think the same thing happens for the DNA storage right now. People are developing the techniques, how to construct the arrays. Of course, the things are a little bit different, but anyway, Now this code has rate. So there are three bits going and 5 bits are coming out. So rate will be what? 0.6, right? 3 by 5 is 0.6. Code efficiency we can define. So what is code efficiency? I should mention. Code efficiency is equal to code rate divided by capacity of the key constraint channel. Okay, having the same run length, having same run length constraint. Okay, this will be something around 0.6 divided by 0.695. Sorry, 94 actually, equal to 0.6 divided by 0.694, equivalent to 0.86. So this is kind of pretty good efficiency for this, such a simple thing. And so I think I'm purposefully not giving you the actual construction for how to. I'm just allowing you to think, you young brain, to how do we construct such things, okay? With a good efficiency thing, right? Because if you can construct a little bit of things, it will lead to something new in the DNA storage thing business also, right? So I'm just leaving it as an thinking for you. How do we construct this? Of course, if you want, there's a whole book. Even I think Ronnie, yeah, this Israeli person, Liman Roth, he has written a constraint codes for masked media storage. Whole book is available. You can find it out. A lot of things are given there, bounds, this and that, and so on. But you see, again, depending on the kind of constraints you want, it will lead to new kind of theory, right? And new kind of applications, right? You want to look at the capacity and everything and all those things in that scenario. So now I think we'll focus on the DNA storage, what we have looked at it. Any idea why this constraint codes will be useful for our scenario of DNA storage? So you see, in the DNA storage business, we are putting a constraint that no consecutive runs of length 1 should appear, right? Exactly same problem, right? So now how do we handle this, And initially when we looked at this problem, so now what we did actually, I mean, this paper you can read actually in IEEE communication letters. And I think still I'll mention what are the things that you can still do here further. So we identified bunch of, so there are two things here we have done. So first thing that what we have done in this paper, we have counted how many vectors are there of over ACGT of certain length, and such that repetition is not there. So repetition of this homopolymer things are not there. So basically AA, CC, GG, TT is not there anywhere in all. Number one condition. Number two condition, the GC content should be certain fixed. So number of occurrence of G and C in any code word is say U in general. So roughly we, for the practical purposes, we take around n by 2 length, just half of the length. Okay, that is the ideal situation. Okay, in some cases people look at 60%, 50%. 50% is the ideal thing. Over the, if whole length of the string is n, we take n by 2. Okay, so this is something very, very important. But from mathematical point of view, you can always ask what will happen if the number of occurrence of G and C in each code word is U or W, whatever, right? So how many of them are there? Here we give a bound. So first of all, actually, we first computed how many of these are there, and then we gave a bound on these kind of codes, so a lower bound on these kind of codes, okay? And then we also give a algorithm known as heuristic algorithm for construction of these vectors, okay? So now let us look at these two things. So this is a, first of all, heuristic algorithm to generate DNA code words. So we generate 4 into 3 minus 1 code words over quaternary alphabets. Then remove the code words from the list that do not have GC content W, that fixed number W, right? And I'll show you that formula. Number of such code words is given in theorem 1. I mean, I'll show you that formula. Now for each code word in the list, count all the code words at a distance d minus 1 in a sphere. Okay, you form the sphere remove the code word, the maximum number of code words in radius d minus 1, reduce the number of code words at distance d minus 1 by 1 for all code words that were within the distance d minus 1 of this removed code word. So all these calculations, I would again giving you an exercise to really better understand for you. Just work out a small example, say for length is equal to 4 or maybe, 4 will be okay, I guess, yeah. For length is equal to 4, just work out what is happening, okay, as an exercise. So you will see what is happening, right, in the algorithm. Okay, you just do it. So once we implement it, we get this kind of code word, for 8 to 89, 3. Okay, so obviously it's I think this is just improving the bounds at that time what was available on the homopolymer constraints, and we also showed that it will give you 166 exabytes per gram of DNA. This result is important, the first one. The number of code words of GC weight U with no repetition constraint. So repetition is not there of AACCGT is this formula. The proof of this formula in the paper is a bit clumsy and very lengthy. Okay. So now again I am asking you, and this is kind of, we try to find a simple formula. I will give you a hint and clue and see if you can actually find a simple formula. In the case, say when U is equal to n by 2, because U is, the fixed number of GC occurrence, right? So when it is n by 2, which is the ideal case, I'm assuming that this is the ideal case, then you can actually, I think you don't have to look at the proof of this thing. So there is a way of counting actually. So you need to probably invent a new way of counting. So all your discrete math skills that you learn will be useful here. How do you count actually? Okay, and that will give you a nice formula. So I'll tell you why this is happening. Okay, so once we count this, then the minimum number of code words of length n GC weight U and a minimum distance d is bounded by this. When we put the constraint of d, so these things are bounded by this number. Okay, so this is important thing. Okay, and I think probably we can simplify this. So let me show you the comment we received by Kizimik himself. He read our paper and then he wrote this email to us that 20, this is the equation 20, that B and W. Here I have used W rather than U anyway. That's okay. For W is equal to n by 2, n even. So basically we are looking at balance sequences. GC occurrence is balanced, right? Total n by 2. So for n is equal to, what he did, he put n is equal to 2, 4, 6, 8, 10, and he get a series like this: 8, 56, 424, 33, something like that. You divide it by 4. So divide these numbers by 2 actually, you get this series: 4, 28, 212. As I mentioned, I think I have shown you Sloan integer sequences, right? That database where you can actually search for sequences and see a new proof or something, new light. He also did the same thing. He saw that he entered this sequence into the Sloan encyclopedia and he found this sequence, So now he's asking this question. Now that sequence can be generated by simple expressions. Okay, the expressions are simple there. I mean, look at the, I think I'll show you that. This is the thing, online encyclopedia of integer sequences. So there are formulas are given here, right? Simplicity. So the thing is that this is coming from counting two-dimensional directed walks on a semi length and starting at 0, 0, 0. So some sort of counting, So we need to simplify the formula Bn comma W, where W is equal to n by 2. Forget about the proof given in the paper. Some other way of counting, which we have got. So we got some hint here how they are counting these things. If you can arrive at that counting by some other simple mechanism, that will be interesting. I mean, that can be published as well, right? It's something interesting. So I invite you to look at it, because I think we all looked at it, and I think we could not do it yet. So basically, you need to invent new kind of counting, as he's mentioning, Because see, the counting which was given in our paper is not simple actually. It's very difficult, but lengthy actually. So here, can we have a simple expression, same expression, but counting in a different manner? And the connection is given there, right? So I think I invite you to look at it and see if you can actually do it. Okay. So there was a table improvement in the constraints using elastic algorithm. You see the improvements, the red ones, okay, which was known to the lower bounds. And or we plotted the rate and everything, So I talked about run length coding. I have given you, right, an exercise. If you remember, these are very important exercise, Huffman coding, binary, Huffman coding, ternary, I have not taught, but at least you have some idea in a similar way. Gole code I talked about. Constraint coding, I gave you an idea. What is left is Reed-Solomon. So I'm going to talk tomorrow about Reed-Solomon codes, their construction and how they are used in the DNA storage thing, right? So each segment is very, very, Reed-Solomon codes are also used, quite useful actually in the storage, right? So Reed-Solomon and constraint coding, both are very, very important, right? And there's a lot of low-hanging fruit available here. Okay, so I think if you think it carefully, you may arrive at something interesting. Okay, if you want to know any more references or anything, just please let me know, and I will actually give you that reference or anything about anything, right? So I think that's all for today. So tomorrow we are going to talk about Reed-Solomon, because this is very important. There a lot of work has been done on this Reed-Solomon business, and then we'll see. Slowly we'll go to the other parts of the codex. Okay. Okay. Thank you. So these things which I am giving you as an exercise, of course, this is a difficult problem, but if you can come up with a solution which is nice, but there are certain things which I am giving, I may ask also, right, in the exam, right? So I think you just make sure that you are doing it. I think there are only these many people, right? So I don't know what about the others, but anyway. Okay, the first exam is there in September somewhere, right? 12th or something? Huh? 30th, fine.